ninth lecture on basic quantum mechanics. Today, we will be discussing some general issues regarding the eigenvalues and eigenfunctions for the one-dimensional Schrodinger equation. In my last lecture, we had solved the problem of an electron or a proton confined in a potential well of infinite depth. Essentially, we had solved the Schrodinger equation for a particular form of the potential. And as I had mentioned earlier, a major part of quantum mechanics, non-relativistic quantum mechanics, is essentially obtaining the solution of the one-dimensional and the three-dimensional Schrodinger equation for different forms of the potential. So, as we had discussed in our earlier lectures, that the one-dimensional Schrodinger equation is given by I h cross delta psi by delta t is equal to h psi, psi as a function of x and time, and h psi of x t is equal to h cross square by 2 mu delta 2 psi by delta x square plus v of x times psi. This is known as the one-dimensional Schrodinger equation for the free particle, for the particle in a potential energy function v of x. We assume that the potential energy function is independent of time, depends only on the space coordinates, and then as we had discussed earlier, we can write down the solution using the method of separation of variables, which is given by psi of x and t of t. We had done this before and we found that the variables indeed separated out, and the time dependent part was given by e to the power of minus I e t by h cross, where e is a constant. So, if we indeed substitute this, we would obtain the following equation, that minus h cross square by 2 mu d 2 psi by d x square, because now the small psi depends only on the x coordinate, plus v of x psi of x is equal to e of x, e of psi. So, this equation is actually an eigenvalue equation, because we can write this equation in the following form, that h psi is equal to E psi, and where H is the Hamiltonian operator, which is the kinetic energy p square by 2 mu plus v of x, and if I substitute for p is equal to minus h cross delta by delta x. So, we will get minus h cross square by 2 mu delta 2 by delta x square plus v of x. This operator representation for the total energy, this is known as the Hamiltonian. This is known as the Hamiltonian of the system. So, my Schrodinger equation is usually written as the time independent Schrodinger equation is written as an eigenvalue equation. So, if I substitute this here, so as was obtained a few minutes back, minus h cross square by 2 mu, since psi depends only on the x coordinate, I can replace the partial differential operator by a total differential operator d 2 psi by d x square plus v of x psi of x is equal to E times psi of x. As I had mentioned earlier, this is an eigenvalue equation. Even this equation is an eigenvalue equation. We will find that for a given potential energy distribution, only certain discrete or continuum values of E are allowed. Those are the eigenvalues of the problem, and corresponding to each eigenvalue, there is a wave function. Those are known as the eigenfunctions of the system. So, we can write this equation, rewrite this equation, just a simple ordering d2 psi by dx square plus 2 mu, where mu is the mass of the particle, E minus V of x. In most textbooks, the equation is written either in this form or in this particular form. Now, in my last lecture, I had assumed V of x to correspond to a particle in a one dimensional box, and we had assumed the particle to be confined between x is equal to 0 and x is equal to a, let us suppose. And we had found that the energy eigenvalues are given by E n, which was equal to n square pi square h cross square by 2 mu a square. This is equal to n square E 1, where E 1 is the energy level corresponding to n equal to 1. So, that is the ground state energy value 2 pi square h cross square by 2 mu a square. And the corresponding wave functions was given by psi n of x was equal to under root of 2 by a sin n pi x by a, where n takes the values 1, 2, 3, etc. Today, we will discuss some general properties of the eigenvalues and eigenfunctions for a given potential energy function V of x. For example, we will show that all eigenvalues must necessarily be real. Secondly, we will show that eigenfunctions corresponding to different eigenvalues are necessarily orthogonal. So, let us first prove that the eigenvalues are always real. So, we write the eigenvalue equation. So, d2 psi by dx square, let us suppose for the nth state. In my previous problem, you remember that we had explicitly determined the energy eigenvalues. So, this is my ground state, this is the first excited state, this is the second excited state, this is the third excited state, n equal to 1, n equal to 2, n equal to 3, n equal to 4, etc., etc. So, we assume we do not take a specific form of V of x. For a general V of x, we assume that psi n of x is an eigenfunction belonging to the eigenvalue 2 mu by h cross square E n minus V of x psi n of x is equal to 0. I now write the complex conjugate of this equation. So, if I take the complex conjugate, so we will have d2 psi n star by dx square. Mass and h cross are necessarily real quantities. So, you will have 2 mu by h cross square, and let us suppose E n can take complex values E n star, but the potential energy function is a real function of x. So, the complex conjugate of that is the same as V star of x is equal to V of x multiplied by psi n star of x. So, the second equation, equation number 1 is the Schrodinger equation corresponding to the nth eigenstate. Equation number 2 is the complex conjugate of equation 1, where we have assumed that the potential energy function is a real function. What I do is I multiply the first equation. And usually the convention is you multiply on the left by psi n star, and the second equation on the right by psi n, and then subtract. So the left hand side, the first term will be, if you see this carefully, psi n star d2 psi n by dx square minus psi n d2 psi n star by dx square plus 2 mu by h cross square. Please see this, here also it is psi n star psi n, here also it is psi n star psi n. So, if you subtract this from this, the v will cancel out, we will have E n minus E n star multiplied by psi n star psi n equal to 0. This term, if you write carefully, then it will be the total differential d dx of, please see this, psi n star d psi n by dx minus psi n d psi star by dx. Straightforward differentiation of this equation will give, the first term will be d psi n star dx d psi n by dx, and then the second term will be psi n star d2 psi n by dx square. And if you differentiate these two terms, then it will be minus d psi n by dx d psi n star by dx, and then this term will come minus psi n d2 psi n star by dx square. So, obviously, these two terms will cancel out, these two terms will cancel out, this term will remain, So, these two terms will be psi n star d2 psi n by dx square minus this. So, this quantity is rigorously equal to this. So, what I do is I integrate this plus I integrate this plus I integrate this. So, I will obtain, if I integrate a total differential of a quantity multiplied by dx, of course. So, we will get psi n star of x d psi n by dx minus psi n d psi n star by dx, this plus 2 mu by h cross square. I can take this outside, and then integral mod psi n square dx. So, this is equal to 0. So, from minus infinity to plus infinity. So, this I take the limits from minus infinity to plus infinity. For any practical problem where you have a localized particle, the wave function and its derivative must go to 0 at the boundary. These are the boundary conditions of the problem. So, this quantity at both the limits will be 0. So, this will be 0. So, we will obtain this quantity as 0. So, we will have 2 mu by h cross square, which is just a number which can be removed, E n minus E n star integral minus infinity plus infinity mod psi n star dx is equal to 0. Now, this quantity is positive definite, because this is the square of a wave function. In fact, the wave function we always assume to be normalized. So, that this quantity is always equal to 1, we can always assume to be equal to 1. So, therefore, and this is a constant, this is a constant. So, you must have E n star must be equal to E n. That is, all eigenvalues of the Schrodinger equation must necessarily be real. All eigenvalues, all, this is an important result, all eigenvalues, we will come back to it when we discuss the Dirac-Brillouin-Ket algebra, but all eigenvalues of H, the Hamiltonian, are real. And as we will discuss later, that if you make a measurement of energy, then you will obtain one of the eigenvalues of H. So, these are the possible values that we will measure if we make a precise measurement of energy. So, we have proved that the energy eigenvalues are real. What we will next prove is that if E n, if there are two eigenvalues E n and E m, and if these two are not equal, then the corresponding wave functions psi n and psi m. So, we will have psi m star x psi n of x dx taken between minus infinity to plus infinity, this will be equal to 0. When this condition is satisfied, we say that the two functions are orthogonal. So, this is known as the orthogonality condition, orthogonality condition. Now, the proof is very simple. We write the Schrodinger equation for the nth state d2 psi n by dx square plus 2 mu by h cross square, mu is the mass of the particle, E n minus v of x psi n of x is equal to 0. Then I write for the mth state. So, d2 psi m by dx square plus 2 mu by h cross square E m minus v of x psi m of x is equal to 0. What we do is, we take the complex conjugate of the second equation. So, I take the complex conjugate of the second equation, of course, mu and h cross are real quantities, numbers. E m we have proved just now to be real. So, E m star is equal to E m. So, we do not have to do anything there, and then we take the complex conjugate here. There is nothing here, sorry. So, because E m is a real number, and then what we do is do the same trick as we had done before, multiply this by psi m star on the left, the whole equation, and multiply this equation by psi n on the left, right. So, if you subtract, if you multiply the second equation by psi n of x and then subtract, then as we had obtained in my earlier slide, we will obtain psi m star d 2 psi n by dx square minus psi n d 2 psi m star by dx square plus 2 mu by h cross square. Please see this, psi m star psi n, psi m star psi n. So, v and v are the same. So, these two terms will cancel out. So, I will be left with E n minus E m psi m star psi n equal to 0. So, what we do next is, as we had done in the previous slide, I write this as a total differential d by dx psi m star d psi n by dx minus psi n d psi m star by dx. Let me leave some space here, and the same quantity 2 mu by h cross square E n minus E m psi m star psi n. I now multiply by dx and integrate from minus infinity to plus infinity. I now integrate from minus infinity to plus infinity dx, this is equal to 0. I had done this in my last slide, that if you expand this out, there will be 4 terms, 2 of them will cancel out and the remaining 2 terms will be this. So, this will be psi m star d 2 psi n by dx square minus psi n d 2 psi m star by dx square, and then there will be terms like d psi m star by dx, d psi n by d, and d psi n by dx, these 2 terms will cancel out. So, this is the differential of a of a quantity, so that the integral is just this quantity, and so therefore, the left hand side after carrying out the integration will be just psi m star psi n prime, that is the differential of psi n prime, psi n minus psi n psi m star prime taken between minus infinity to plus infinity. Now, this is 0, because the wave function vanishes at infinity. For them to be square integrable and normalizable, they must vanish at infinity. So, by square integrable I mean any function psi n of x is square integral, means mod psi n square dx from minus infinity to plus infinity must be finite, and I will choose a multiplicative constant, so that this is equal to 1. So, a function which satisfies this equation, or this actually the equation that this quantity the integral should be finite, is known as a square integrable function. And for a square integrable function, the function itself must vanish at infinity, otherwise it will not be a square integrable function. So, therefore, the wave function and its derivative must vanish at infinity, and so therefore, this term will be 0, this will be equal to 0. So, we will have only, so if this term is 0, so I can cancel this out, I will get this is equal to 0. So, I will have product of two terms, if I write this E n minus E m multiplied by this. But I have initially assumed that E n is not equal to E m. Therefore, this integral must be 0, and this integral minus infinity to plus infinity psi m star of x psi n of x dx must be 0 when E n is not equal to E m. This condition, as I had mentioned earlier, is known as the orthogonality condition. Orthogonality condition. I am assuming that the wave functions are normalized. Therefore, minus infinity to plus infinity mod psi n square dx is equal to 1. So, this is known as the normalization condition. Normalization condition, and I can combine both of them to write down this equation, integral from minus infinity to plus infinity psi m star of x psi n of x dx is equal to delta m n, where this term delta m n is known as the Kronecker delta function, and this is equal to 0 if m is not equal to n and is equal to 1 if m is equal to n. So, we have derived an extremely important result, that the wave functions belonging to different eigenvalues, are necessarily orthogonal, and this is the orthogonality condition. There is one more thing that I would like to mention, that we will use this, that the wave function, that the eigenfunctions of the Hamiltonian form a complete set of functions. That means, if psi n of x, let us suppose in a particular problem we have a set of wave functions which are the eigenfunctions of the operator h, then any arbitrary function, say phi of x, any arbitrary well behaved means it has to be single valued, it should not be infinite anywhere, and it should be a square integrable function. So, that is the meaning of the word well behaved, that it should be single valued function at a particular value of x, phi of x must have a unique value, it must not have any infinities, it must not go to infinity and at any point, and it is a square integrable function, that is phi of x dx integral from minus infinity to plus infinity must be less than infinity. This symbol means, this inequality means that this integral is finite. So, such a function is known as a well behaved function, and I state without proof that the eigenfunctions form a complete set of functions, that is any arbitrary function can be described. I will give you examples of that, C n psi n of x. So, this is known as the completeness condition, that any arbitrary function can be represented as a sum, as a linear combination of the eigenfunctions of H. So, how do I determine Cn? What we do is, I multiply this equation by psi m star of x dx and then integrate. So, what we will have is that the left hand side becomes psi m star of x phi of x dx is equal to summation, the sum is over all values of n, the Cn psi m star of x psi n dx integral from minus infinity, all limits are from minus infinity to plus infinity. But this I have just now proved to be equal to delta m n. So, therefore, this equation becomes, the right hand side becomes C n delta m n. The summation is over all values of n. So, only the n equal to m term will survive, because for all other terms this Kronecker delta function is 0, as I had mentioned that delta m n is equal to 0 for m not equal to n and is equal to 1 if m is equal to n. So, therefore, the summation is over n. So, when n takes the value m, that term survives. So, this will be equal to C m. So, this is how we will determine the coefficient, as I had indicated in my earlier lectures also. So, C m is equal to, or I can write down C n is equal to integral, and these limits are also from minus infinity to plus infinity, psi m star of x phi of x dx. Sorry, n, this should be n. Now, what I do is, next step is, I substitute for C n from here to here, but you must be careful, because this is a definite integral over x. This x should not get confused with this x, but since this is a definite integral, I can quietly put a prime here, and then this x and this x can be differentiated. I hope it is clear, because this is a function of x and C n is a constant, and C n is a definite integral, and in a definite integral it does not matter whether you write x or y or z. For example, e to the power of minus x square dx from minus infinity to plus infinity is the same as e to the power of minus y square dy. It does not really matter what both of them are equal to square root of pi. So, this x should not get confused with this x, and so therefore, I quietly put a prime, and then I substitute this here. So, I will substitute this expression for C of n in this equation. So, I will obtain, please see this carefully, that phi of x is equal to summed over n and C n. And what is the value of C n? As we had determined earlier, minus infinity to plus infinity, psi n star x prime phi of x prime dx prime multiplied by psi n x. What I will do is, I will first carry out the summation and then the integration. So that all these quantities which are dependent on n, I take this. So, I get summation is equal to integral from minus infinity to plus infinity. Please see this carefully. Phi of x prime, phi of x prime, and then some function of x comma x prime dx prime, and as you would have noticed that f of x prime, f of x comma x prime is the summation of psi n star x prime multiplied by psi n of x summed over n. If you would recall the earlier lectures, one of the earlier lectures in which we had defined the Dirac delta function, and that was phi of x will be equal to minus of infinity to plus infinity phi of x prime delta of x minus x prime dx prime. So, it picks up the value at x only, no matter what the function phi is. So, therefore, this function has to be 0 for all values of x other than x prime, and so therefore, this quantity must be the Dirac delta function. This condition is often known as the completeness condition. That is, the wave functions, the eigenfunctions of the Hamiltonian operator form a complete set of orthonormal function, and we say this through the following equation, that summation psi n star of x prime psi n of x summed over n is equal to delta of x minus x prime. So, we have derived two very important relations. This is known as the completeness condition, and the other is that psi m star of x psi n of x dx is equal to delta m n. This is known as the orthonormality condition. It combines the orthogonality condition and the normalization condition. So, this is known as the orthonormality condition. Okay. So, these limits are also from minus infinity to plus infinity. So, now in the example that we had discussed in my last lecture, lecture 8, we consider a particle in a one dimensional box, and the domain that we considered was between 0 and a, and we had found that the energy eigenvalues are E is equal to E n, n square of E 1, where E 1 is equal to pi square h cross square by 2 mu a square. These are the eigenvalues, and as you can see, all eigenvalues are real. We had also derived that the wave functions are given by under root of normalized wave functions sine of n pi x by a. And if you use this, you can immediately show that psi m star of x psi n of x, if m and n are different, then it will be 0. So, this is equal to delta mn. So, we have E1, E2, E3, E4, E5 and so on. There are infinite number of states, infinite number of discrete states, and any function, any well behaved function in the region from 0 to a can be represented by, can be approximated, and this is my Fourier series, that C n psi n of x. So, this is something like the Fourier series that you must have learnt in your college. So, the wave functions also form a complete set of functions, and so therefore, psi n star x prime multiplied by psi n of x summed over n equal to 1, 2, 3 infinity is equal to delta of x minus x prime. So, this was the particle in a box problem that we had done yesterday. Let me consider another problem. About 3-4 lectures back, I had discussed the free particle problem. Now, in the free particle problem, let me do it on another sheet. V of x is 0 everywhere. So, it is a free particle, and the Hamiltonian operator, which is equal to minus h crosses p square by 2 m, h crosses square by 2 mu d2 by dx square plus v of x, but v of x is 0. So, we had solved this equation and we had found that if I write h psi is equal to E psi, then we will get d2 psi by dx square plus 2 mu e by h cross square psi is equal to 0. So, if I write h psi is equal to E psi, then simple manipulations will give this, where E is now the eigenvalue, where it is a number. So, we write this as p square, this quantity as p square, and the eigenfunctions are psi of x becomes psi p of x, this is equal to e to the power of I by h cross p times x. Now, I put, because I know this, I put a factor 2 pi h cross. So, what are the values of p? E has to be positive. E has to be positive, because I put, because if E becomes negative, as you can remember, as you can see, p square is equal to 2 mu E. So, if E becomes negative, then P will become imaginary. If P will become imaginary, then times I will be something like either plus or minus kappa x. When this happens, then the wave function either goes to infinity at plus infinity or minus infinity. E to the power of plus kappa x will blow up at x is equal to infinity as x tends to infinity. E to the power of minus kappa x will blow up as x tends to minus infinity. So, that is not possible, because if the wave function becomes infinity, it is no more square integrable. You can no more normalize the wave function. So, therefore, E has to be positive, but P can be plus or minus. So, for a given value of E, there are two values of P, one plus, one minus. We say that there is a twofold degeneracy. So, if you work this out, then I can write down that psi p prime of x will be equal to 1 by 2 pi h cross e to the power of I by h cross p prime x. Please see this. If I take a star here, make the complex conjugate, then this will be minus here, and I can write down psi p prime star x psi p x dx minus infinity to plus infinity. I multiply this. So, I get 1 over 2 pi h cross e to the power of I by h cross p minus p prime times x dx from minus infinity to plus infinity. So, this is the Dirac delta function, delta of p minus p prime. This is an example where the eigenfunctions form a continuum. In the previous example, we had a discrete set of energies. Only certain values of energy were allowed. In this case, we have all possible values of energy from 0 to infinity. So, we say that the energy eigenvalues form a continuum. Energy eigenvalues are 0 less than e, they can take all values between 0 and infinity. So, they form a continuum. And when this happens, the orthonormality condition is represented by this equation, psi p prime star of x psi p of x dx. The Kronecker delta symbol is replaced by the Dirac delta function. Also, these functions, of course, they form a complete set of functions. So, that any arbitrary function phi of x can be written as a of p superposition times psi p of x, psi p of x dp. And so, therefore, these limits are also from minus infinity to plus infinity. So, what is psi p of x? Psi p of x is 1 over root 2 pi h cross integral a of p e to the power of I by h cross p x dp. So, this is the Fourier transform. So, it is a superposition of the moment of these wave functions. And so, therefore, a of p is given by the inverse Fourier transform, which we had discussed in quite a bit of length. This will be phi of x e to the power of minus I by h cross p x dx. All limits are from minus. So, for any well behaved function phi of x, I can always make this expansion, because I can always find a of p by carrying out the inverse Fourier transform. Now, I can substitute for a of p in this equation, but I have to be careful once again. This is a definite integral over x, and this x should not be confused with this x. So, I must quietly once again put a prime here, and when I substitute that, I will obtain, if you see this carefully, that if I substitute a of p from here to there, then you will get phi of x is equal to 1 over 2 pi h cross phi of x prime, and then there will be another function x comma x prime dx prime, where f of x prime comma x prime is equal to, I will take the 1 over 2 pi h cross here, 1 over 2 pi h cross integral e to the power of I by h cross p x minus x prime dp. This we know that this is the delta function. So, as soon as I substitute it here, I get phi of x. So, this is my completeness condition. It is no more a sum, it is an integral. So, psi, this condition that I represent, this is the completeness condition, integral e to the power of I by h cross p dp from minus infinity to plus infinity is equal to delta of x minus x prime. This is the continuum eigenfunction of the this is the completeness condition for the eigenfunctions of the operator H. I would like to mention one more thing, and that is, let me consider the momentum operator P op. The momentum operator, we had said that the momentum operator can be represented by minus, I write it as a total differential. And let us try to find out the eigenfunctions of the momentum operator. So, I write this as P op psi is equal to P psi. This is an eigenvalue equation for the momentum operator, where P is an eigenvalue which is just a number. So, we had the eigenvalue equation H psi is equal to E psi. This is the Hamiltonian, which is an operator, and you find that only certain values of E are allowed. These are the eigenvalues. So, you have the momentum operator P op, and this is a, I want to solve this eigenvalue equation. So, I will have minus I h cross d psi by dx is equal to P psi, where P once again is a number. So, I multiply by I by h cross. So, the left hand side becomes 1. So, I get 1 over psi d psi by dx is equal to I by h cross times P. If you integrate this, so you get log psi is equal to I by h cross P times x plus a constant. So, psi becomes the constant I will choose as 1 over under root of 2 pi h cross e to the power of I by h cross p x. So, these functions psi of x, I write this as psi p of x, and I have put the factor 2 pi h cross e to the power of I by h cross p x, where p can take any value from plus infinity to minus infinity to plus infinity. These are known as the normalized momentum eigenfunctions. These are known as the normalized momentum eigenfunctions. These are the eigenfunctions, normalized eigenfunctions of the momentum operator. Actually, these are simultaneous eigenfunctions not only of the momentum operator, but h psi is equal to E psi for the free particle. So, therefore, we say that psi p of x is equal to 1 over root 2 pi h cross e to the power of I by h cross p x, p going from minus infinity to plus infinity. They are simultaneous eigenfunctions, of p op, which is equal to minus I h cross d by dx, and also of the Hamiltonian for the free particle. Hamiltonian for the free particle is h cross square by 2 mu d 2 by dx square. Actually, the Hamiltonian has a v of x term, but v of x is 0. This is for a free particle, and these wave functions are therefore eigenfunctions of p op as well as of this, and these wave functions are often known as the momentum eigenfunctions. And they form a orthonormal set, that is psi p prime star x psi p x dx is equal to the Dirac delta function p minus p prime, and they also, all limits are from minus infinity to plus infinity, and they also form an orthonormal the completeness psi p of x psi star p of x p prime psi p of x dx, this is equal to delta of x minus x prime, sorry psi p is x prime here, and this is the orthonormality condition, this is the completeness condition. Let me rewrite this again. This is not, I have not written this carefully. So, this is integral psi p star of x prime times psi p of x dp is equal to delta of x minus x prime. This is the completeness condition. So, this completes the analysis for the free particle problem as well as for the particle in a box. In our next lecture, we will discuss first the solutions of the linear harmonic oscillator problem, and then we will derive those solutions. Thank you.